Hello everyone, welcome to this webinar on hardware in a loop for microgrids. My name is Steve Liu and I am an application engineer in electrification at Speedgoat. Joining me today is Jonathan Lasage from MathWorks. In today's webinar, we will go through the following. Why do we want to use hardware in a loop for microgrid? What are the benefits? What solutions can Speedgoat and MathWorks provide? Then we will follow with some examples. Jonathan will show you how to use Simulink and Simscape Electrical to build a model for microgrid and do desktop simulation. And I will show you how to set up a hardware-in-a-loop system and perform real-time testing. So why do we want to use hardware-in-a-loop for microgrids? What are the benefits? Let's say your company is designing a microgrid, either the entire system or just adding some power generation sources into the current system. And your team's responsibility is to design a PLC control system for the supervisory controls. Here are some questions need to be answered. First question is about safety. How do you want to test your controls? Do you want to directly hook up your controller to the hardware or system before enough testing and analysis? The answer is not. It could be very risky and dangerous to your equipment or even your personal safety. Second question is regarding the planning and the timeline. Is your hardware that you want to control available for your testing? Probably not. A lot of times, your hardware may not be available yet when you want to do the testing. Third question is about cost. You may say, I can build a lab or prototype to do the testing, but it may be costly or time-consuming. On top of that, although those questions may apply to all different industries, for microgrids, these questions are even more important and necessary. This is because of the complexity and the uniqueness of microgrids. A microgrid could have various types of power generation sources like solar panel, wind turbine, diesel generator, fuel cell, etc. It could be remote, it could be running as a standalone or island mode, or could be connected to the grid. Therefore, complying with grid code and ensure safe and smooth transition is very important. Because in microgrid, you will be dealing with high voltage and a lot of different equipment, thoroughly understanding your system and sufficient testing is very important. With HIL testing, you can test your control's robustness by running the system in extreme scenarios or with different system variations with zero risk. To do so, a common practice is to use model-based design, and hardware-in-a-loop testing is a key step for that. Let me show you a bit more detail on how we want to do this with the model-based design and the testing. First, you can build a model of your microgrid system, so you can do simulation. We will show you later what tool to use and how to do this. After you have your model, you can implement it into a real-time target machine, and we will show you later what to choose and how to do it. Now you have your planned model, which represents your real system. From I/O level or communication protocol level, they're running in real time and they behave just like your real plant. The difference is your plant model is virtual. So when you hook up your controller to the target machine, it's just like you're testing your real system. And you can test them over and over again, and you don't need to be worried about breaking the hardware. This is a process of from building a model to testing in hardware-in-a-loop. We call the model, which is running in a real-time target machine, as digital twin. In hardware-in-a-loop, you test your controller against your digital twin. I hope we just convinced you that hardware-in-a-loop is important for your microgrid development and testing. Next, Let's take a look at how Speedgoat and MathWorks can help you to build a HIL system and use it. Following that, we will also show you some demos. Let's start with typical components of a HIL system. There are typically three main components. First, your system under test. This includes the production controller that requires thorough testing, and additional real components like domain controllers, sensors, and actuators. Second, a HIL test bench, including a real-time simulator where you run a digital twin of the plant, together with the emulated plant components and I/O modules supporting data acquisition, signal conditioning, and communications with the system under test. Third, a workstation. You use it to build your simulation model and run application software that supports setup and operation of the HIL test bench. From a system level, when you use Speedgoat for your hardware and then MATLAB Simulink for your software, you will work in one unified environment. Software and hardware are designed for one another, shielding you from interoperability issues. You operate your HIL setup from the same environment where you design your controls and automate your tests. The environment is MATLAB and Simulink. Under the hood, the two main components, Simulink real-time and Speedgoat hardware, work hand in hand. Later in this webinar, we will show you some demos. After those examples, I hope you will understand more why we call it as a unified solution. When it comes to modeling, there are various toolboxes to serve microgrids needs. Those toolboxes also provide a lot of ready-to-simulate reference examples. You could make your modeling and simulation quicker and easier. For microgrids, one of the most important and powerful toolboxes is SimScape Electrical. You could cover different power sources like solar panel, wind turbine, fuel cells. You could cover power transmission lines and distribution. You could cover electrical machines, power electronics, and a lot more. With those teams, we maintain a very close collaboration. For instance, SimScape Electrical currently ships with 50+ examples that are compatible and fully tested with Speedgoat hardware. When it comes to the hardware, HIL Simulator is a core component. Benefit from a wide range of real-time target computers that can operate as HIL simulators. The mainstay of HIL testing is the performance machine. It's the most scalable and performant system. It's suited for desktop use, but also suited for rack mounting. The mobile, baseline, and unit machines are smaller and ruggedized, making a better fit in HIL applications that require more portability and less I/O channels. Speedgoat target computers come with multi-core processors, supporting concurrent execution and code simulation with FPGAs. They run a QNX-based real-time operating system that supports certification with high-integrity safety standards. There is also extensive onboard connectivity, including a varied set of Ethernet-based protocols, serial and video interfaces. The PCI Express architecture serves as the backbone for the I/O connectivity with the lowest latencies and support for direct memory access and FPGA-based I/O. You can also update and scale your system at any time with I/O expansion units or by implementing distributed simulation architectures, as we will be seeing later. With the help of our project management and productions teams, we can provide you with fully customized rack systems, including rack-mounted HIL simulators and easy access to all signals via breakout and I/O panels. We will integrate power supplies, actuators, inverters, and any kind of power electronics, as well as project-specific PCBs for signal routing and conditioning. Using Speedgoat I/O is easy. A key enabler for this is the stress-free I/O configuration. I/O and hardware of any kind is represented by Simulink blocks. Placing them in your model and configuring them is very simple. And the compatibility with the Simulink library block is always guaranteed. Many of our I/O modules allow reconfiguring I/O capabilities of your HIL simulator from Simulink without swapping any hardware. Thereby, you can adapt to new needs and optimize your investment. You can use the same hardware for different projects. Documentation and examples are accessible with a few clicks and directly integrated into your MATLAB documentation. Speedgoat I/O modules support most industrial communication protocols for buses and networks. Here are highlighted the ones that are typically used for microgrid testing. I/O solutions also support emulation of various plant components such as battery cells using battery cell emulation units. You can stack several of these modules to build a HIL simulator of full battery energy storage systems, or BESS, and complement it with failure simulation and temperature cell units. So you can simulate battery packs down to the cell level and employ that, for example, to test your BESS controllers. We can also support you with virtual commissioning of large-scale plants like industrial installation, wind farms, and power grids. For instance, the industrial Ethernet multi-node simulator, as the ones shown here in the picture, lets you virtualize up to 32 nodes like Profinet slave devices. Besides the controller hardware in the loop, there is another type of hardware in the loop that is called power hardware in the loop, or power HIL. In power HIL, you will test your electrical equipment via a high voltage interface like a power amplifier. Speedgoat can support you in building power HIL system, including selection of suitable power amplifiers according to your voltage, power, and bandwidth needs. We will also provide you with a turnkey solution together with our partners. So now you should have had a good picture of how Speedgoat and MathWorks could provide solutions to your HIL project. Let's go through some examples. First, Jonathan from MathWorks will show you how to use MathWorks tools to build a microgrid model and perform desktop simulation. After that, I will show you how to convert the model to a real-time model and then separate it into a PLC controller and a digital twin of the microgrid. And last, I will also separate the model further and let the model run in multi-core environment so that the HIL performance can be more efficient. Now, let me hand over to Jonathan.
Thank you, Steve. My name is Jonathan Lesage, and I'm a application engineering manager with MathWorks. And today, what I'm going to kind of walk through really quickly is how you can use a tool like Simulink and Simscape Electrical to model and simulate microgrid systems, kind of in preparation for hardware in the loop testing of the control systems. So what I have here on my desktop screen right now is a representative example of a simple microgrid. So I've got a couple of components here on my Simulink canvas, different feeders here, utility scale PV array that's connected. And down here, we've got an energy storage system. So I've got the model of the battery itself. And then I have a supervisory control system, which is really going to act to perform peak shaving. And in this particular case, what we're interested in is whether or not our energy storage system here is going to allow us to offset local demands of our microgrid so that we're not putting an excess burden during peak demand times on the utility grid. So I'm going to go ahead and hit this run button. And with Simulink, we're going to be running, and this is actually going to build out the differential equations for this electrical network and perform a dynamic simulation. In addition to the dynamics of all of the components here, we also have the peak shaving control logic. So I'm going to let this run for a little bit. What you'll see here is a scope here that's looking at the load demand from the grid. You can see the active power, the reactive power in blue here, the voltage of the grid, and then the current, the three-phase current coming from the grid. And here we can actually see the demand on the battery responses. So you'll see the voltage of the battery closely mirrors the grid. And during some times, the battery is kicking on and actually providing current and active power. And what you'll notice down here is this is a plot of the cumulative power that's being demanded on by our microgrid. And when that power reaches this currently this green set point here, the energy storage system kicks on, provides that offset or that excess power, making sure that we stay at or below that peak demand point that we're interested in. Okay. Now, I just ran the simulation. We could take a look at these results. I could, zoom in and see kind of that this is a full electromagnetic transient simulation. But I'm going to actually open this up other window here, which is actually the internal contents of my control system here for my energy storage system. And so what this actually is this is a state diagram of the operation that we have for this energy storage system. This is our microgrid controller. I'm going to go ahead and push run again. And like we did before, we could see in the background we had those scopes. Now I actually have my control logic here, the logic that's actually being executed on my microgrid control system so that I can see where we are. Okay, and so that's going to run. We'll see right now we're in grid connected mode. And then eventually, when that demand starts to exceed the threshold, you'll see we've kicked into peak shaving. Couple of other things to note here is I have some other modes here, so I can actually island this microgrid. So now you'll see that I'm getting ready to island. I'm islanded. And if I look at my battery loads now, you'll notice that the current, basically the full demand of this feeder is being provided by the battery. If I go ahead and go back to grid connected, we're going to, of course, synchronize back with the main grid and then close this breaker here to connect with the grid. Okay, and you could see as I did that, this state chart animated. Okay, so this is one of those benefits of performing simulation is I'm able to actually run this sim, explore, try different things, and see where I am in my straight state control logic. Okay, now I gave a high-level overview of this example and what's going on here, but to maybe go a little bit deeper into some of these components, you'll notice I have these different feeders, and Simulink itself is a block diagram-based representation environment, and what it allows us to do is actually group components together. So for feeder A, if I double-click, I'll go inside of that feeder representation, and you'll see that I have additional components, breakers, and then I've got actually active reactive power loads. And so these are dynamic loads that are varying over time. Right now I have some simulated inputs, but we could feed real data from the field into the simulation directly to kind of more closely mimic something we've seen in the field. Likewise, for our inverter-based resources, our PV array and our energy storage system, we can go under the hood as well. So double-clicking on this block, for example, you'll see that I've got a mask with some parameters that allows me to customize this. But if I go under the hood, and maybe I'll blow this up a little bit bigger, what you'll see is the underpinning or representation of this PV array. So I've got my panels themselves. I've got my inverter. You'll see here's my inverter. And then I've got the inverter controls. And so all of this was kind of pre-built, including the maximum power point tracking routines for this inverter. Now, one thing that I do want to note is as I was running the simulation, I ran it for 90 seconds of time, and the simulation was running, kind of in a pseudo real-time fashion. It was approximately 1 second is 1 second of wall time. And the way I was able to easily accommodate that with multiple inverter-based resources is, in this case, I have them running, instead of having full switch mode for all of the switching devices, I've selected average model. And that allows this to run quickly and easily. You lose some of the effects of the harmonics on the simulation. But for a lot of energy case studies where we're looking at active reactive power, maybe voltages and frequencies, especially for a microgrid aggregate study, that level of fidelity is typically quite good. Okay, and then correspondingly, if I go under the hood here for the energy storage system, you'll see we've got a very similar representation. We've got the battery itself. This subsystem here represents the inverter, and then we've got the controls for that. And so in this case, because this battery system can operate both as a grid following and grid forming controller, we both have a current control loop and a voltage control loop. And depending on which mode we have selected, we're going to activate one or the other. Okay. Now, building these systems, if I go into the Simulink library, you'll notice there's kind of a lot of the base blocks for the control systems. But what we've been using here is the Simscape electrical library. So Simscape is a library built on top of Simulink that has schematic representations of components. And so you'll see we've got hydraulic, magnetic, thermal, and then we've got deeper dive libraries with specific components. So on the electrical side, what we'll see here is we've got all of these components for power electronics, for the grid side, so transformers, lines, and essentially to build this, we just kind of drag and drop components. And so relatively straightforward, but again, the power of the simulation here is I can study effects. I can run this sim again. Again, I islanded it. What I can also do is, as the simulation starts up again, test other bits of control logic. So right now my peak shaving set point is at, it looks like 10 kW, so or 10 megawatts. So what I'm going to do is I can decrease it, and you'll see here now we can see how the control system will perform with a different set point there. I could, of course, increase it up. And, of course, now the energy storage system should most likely never be active. And so simulation allows you to test many different things, right? And inject faults. You'll notice I have a fault here. I could inject a fault to see if this microgrid controller reacts to that properly, and allows me to test many things in simulation. Now, the last thing that I want to mention is this control chart here. We've seen it kind of perform run in simulation. One of the things we can also do here is actually convert this over to code that we can deploy directly to hardware. So C, C++, for example, if we're going to be targeting a real-time operating system, or if we want to target some type of industrial PLC or microgrid controller, we can generate PLC code directly from this. And that's going to be IEC 61131 structured text that can then be deployed directly. Okay. So I'm going to pass it back to Steve, who's going to now talk more about hardware in the loop and how we can take the simulation and have it run in real time.
Thanks, Jonathan. Now, Jonathan just showed you how to build a microgrid model by using Simulink and Simscape. And he also saw the simulation results. So the model works good in offline or desktop mode. Now we need to use this model to do the real-time simulation for hardware in the loop testing. Let me show you step by step by going through some examples. First of all, the purpose of HIL is to test your hardware. It could be your controller or some power electronics. To test your hardware, you have to have the model running in real time. So the first step is to convert your model into a real-time model. Then check if the results are correct. In order to compare the results, I'm going to use the same model with the same inputs so I can do easy comparison. Right now, the model has everything in it, which includes the plant and the controller. What I really need to run in the target machine is the plant model. So I need to separate the model into plant and controller. After that, I need to set up the interface between the controller and the plant model so they can talk. After the handshaking or communication is established, then you can go ahead and test your controller. In the end, I also want to show you how to further improve the CPU performance by multi-core simulation for concurrent execution. In this example, I'm going to test a PLC controller for peak shaving control. I'm using a Siemens S7 PLC as an example. But in your case, it could be your own controller. So this is just a placeholder for your application. The plant model will be deployed in a real-time target machine. In this case, I'm using Speedgoat performance machine, which has i7 quad-core CPU. Depending on your application, you can also add different Speedgoat I/O cards like analog I/O, digital I/O if needed. In this demo, to simplify it, I'm passing all the I/O signals through Profinet communication. The Profinet I/O board I'm using is Speedgoat's IO752 card. Now let's do the first step. Convert the model from desktop version to real-time version. What you need to do is to change the model settings from desktop target to Simulink real-time target. You can change the settings in model configuration or just one click from one of the Simulink apps called Simulink Real-Time. When you click the Simulink Real-Time app button, what it does is to change all the model settings for Speedgoat real-time target machine. Now your model is real-time capable, which means you should be able to generate a code, build the model, and run from Speedgoat target machine in real time. First, you set up your real-time simulation system like this. You connect your PC to Speedgoat target machine through Ethernet. With that, you use your PC to generate a code and build the model, and then download your model to target machine. Your model will be running in the target machine. But you can use your PC to monitor the variables and tune the model parameters in real time. Next, you can use Simulink Real-Time Explorer to set up the IP address of the target machine. Then click and select your target machine and connect it with your PC. Once it's connected, you can just hit the Run button. It's one click, but it will start the code generation, compiling, and build the model, and then deploy the model in the Speedgoat target machine and run. Now you can see that the model is running in the target machine in real time. As I mentioned before, you can monitor your variables in Simulation Data Inspector or SDI, which comes with Simulink. And then you can tune the parameters to control the model just like you did in the desktop simulation. The top plot is the power and the bottom one is the current. The red line is for grid and the blue line is for battery. The control function here is so-called peak shaving. Basically, when the grid power reaches the maximum threshold, which is the green dot line here, the battery power will compensate, just like what you saw in the offline simulation that Jonathan did. Looks like the control is working, and it is doing the peak shaving work here. Since I'm using the same model and same inputs and the parameters, I should expect similar results between the two. But let's see. Let's check the results and do comparison. After you finish the run, you can use the Simulation Data Inspector or SDI to do this. You can pick up two runs that you want to compare. One is from the desktop simulation and the other is from the real-time version. Let's pick a couple of signals and take a look. For example, let's look at the battery power. You can see that they are quite close. You can set up your criteria to see how close or how different between the two models. Let's pick another signal, the grid power. The top one is the two traces and the bottom one is the difference. You can see that they are very close to each other too. In this case, let me say it passed. Otherwise, you need to find out why. Now you have converted the model successfully for the real-time version. You can trust this model now. So you can do more testing if you want. For example, I'm trying to see how the model reacts when it's into and out of the island mode. I'm going to flip the island switch here. Now it's in island mode. you can see some power blips at the beginning of the transition. Then the battery power and the current takes over from the grid. So now all the power is from the battery and the power from the grid is 0, which makes sense. When I flip the island switch off, the grid power source will resume and the peak shaving by battery starts again. You see some current spikes here when it's into and out of island mode. Then you can zoom in and to see if it's acceptable or if you need to do something from your controls. Now we're ready for the next step, setting up the PLC controller HIL. First, we need to set up the I/O handshake interface between the controller and the planar model. As we mentioned at the beginning, the I/O handshake interface between the PLC controller and the target machine is Profinet. So we need to set up this interface. What I'm going to do is to go to the Simulink library, and all the Speedgoat I/O block sets are there. I found my I/O 752 Profinet block set. Drag and drop. I need to use a setup block to define the module and the slot. I pack my input signals and output signals. Then I use the receive block to read and the send block to write. Now the I/O handshaking is done and ready to communicate with my PLC. Of course, from a PLC side, we also need to set up the I/O handshaking. Usually it will be you, the user, who configure the PLC I/Os and program the controls algorithm. In this demo, I will set it up. Now, since I need to set this up, just as a side note, what I'm going to do is this. I'm going to use MathWorks PLC coder and right-click on the block, and it will translate the controller algorithm into the code that the PLC needs, which is a structured text file. It's almost like a one-click job. My original control algorithm is MATLAB stateflow. With this PLC coder, the stateflow control will be translated into structured text file, and you can directly import it to your ladder logic. But again, it's your application, it's your controller, and you can do whatever you need for your hardware. Now we are ready to test our PLC controller. Use the HIL simulation. The PLC is running, and the planar model is also running in Speedgoat real-time target machine. In other words, you have your HIL system running. When the model is running, you can still use your PC as the user interface to change the model inputs and the parameters. In this test, I'm going to start the simulation with the island mode first. You can see that all the power is from the battery and the grid power is 0. Then I flip the island switch. Now it's in the grid time mode. Then the grid power takes over and the battery is doing the peak shaving job again. Let me switch back to the island mode again, just for the sake of testing. So you can see that the HIL simulation is working. The results make sense, but the important thing is that you are running your real controller. You can zoom in to see what's happening during the transition. The good thing is that if the current spike during the transition is too big or something bad happened, it won't hurt anything. So you have 0 risk. And you can test it over and over again. As we mentioned, Speedgoat hardware, together with the Simulink real-time, can provide a concurrent execution to further improve the CPU performance and make your hardware-in-the-loop simulation scalable. In the previous example, the entire model is running in a single task. For a large and complicated system, it might overburden the CPU computation. Here I'm going to show you how to divide a microgrid model into smaller subsystems so you can split the task and then run the different tasks in multi-core with concurrent execution. In this model, we're going to split the model into two subsystems. What we want to do is to use the power GUI from Simscape to decouple the two systems. Let me replace this transmission line with the distributed parameter line. Enter how long the line is. I go to the power GUI, then tools, and specify decouple lines. Then select the decouple line which I want to decouple. Now the model has two subsystems. When you use the power GUI to decouple the lines, it will automatically define the send and the receive signals so they can communicate. The next thing is to assign the tasks to the subsystems. I come to the model configuration window and click this configuration tasks button. Here I will enable explicit model partitioning by checking this box. Then I assign these two decoupled subsystems with different tasks. Now let's run the simulation. The simulation is running. Let's look at the CPU utilization. We can monitor this from the TET monitor in Simulink Real-Time Explorer. We can see that both tasks are less than 30% of the scheduled task time. In previous example, which we did not do explicit partitioning, the single task is about 75% of scheduled task time. So now you can see that you let your model run in better efficiency, so it gives you more room to run larger model. This is just an example of scaling up of your HIL simulation capability. As we mentioned before, besides the multi-core simulation, Simscape can also support multi-target HIL simulation by running the model in several target machines by using shared memory with very small latencies. Before we conclude our webinar, let's summarize with key takeaways. First, hardware-in-the-loop testing plays an important role in microgrid design and testing. Not only can it de-risk your integration and testing, but also can speed up your development and save cost. Second, Speedgoat provides a scalable real-time simulation platform with a variety of real-time target computers, wide range selection of I/Os, industrial communication protocols, and FPGAs. Also, we support multi-core and multi-target solutions. Speedgoat hardware, together with MathWorks software, provide you unified real-time simulation and testing solutions. Last, you can use HIL testing to support you in all stages of development and help you to keep the pace of innovation. When you do that, you are also maximizing your investment on HIL. With that, it reaches the end of this presentation, and thank you very much for staying with us in this webinar.
You want to learn more about real-time controls testing? Then find additional content linked here.